Can you guys see my screen?
Yes, now.
You guys see this my screen, slide number 1?
Yes.
Okay, this is a slide I borrow from Wall Street Journal. And you can see today also the weather is quite bad across the United States. There are a lot of power outage, hoping some people think that it will be more than few million people will be having a power outage today. And this is one of the things which we are trying to solve here. My next slide is our goal here in the H2e Power Company to create and distribute the clean and green energy. That's our bigger goal here. The next slide, this is our current model. If you look at the first half of the slide, and you can see this thing, that this is our current model. And here, when we produce power, it also produces the heat. And most of the heat never gets translated to the last mile. So that is wasted. And when we transfer the power from the power plant to the last mile, you can see there is a distribution loss of the power. So we are trying to solve this problem. So if you look at the second half of my slide, what we are trying to do to produce power and heat at the last mile. And we want to decentralize the power grid basically. And that's our long-term goal here. Again, this is 7x24, 365. So we have a system today. We have system running, around 1,000 systems in Europe, and we have a few hundred systems running across the world. We have 3-4 systems running in the United States. But this is our configuration. We have a technology that allows us to produce the power, heat, and hot water at very high efficiency. It can be scalable. We can build a system from 1.5 kilowatt to megawatt. Our system can reduce carbon footprints. It can take basically natural gas today. In the future, it will take a green hydrogen also. And this is a fuel cell technology. The system runs 24/7, 365. The life of the product is more than 10 years. And every 10 years or 5 years, you have to replace the stack, just like a filter. So this is what we are trying to do. We have a scalable model. We can scale from 0.5 kilowatt to megawatt. Our system is very reliable, and it is absolutely noise-free. There is no noise. If you run the system, you will not notice anything in your house or in your commercial building. Any question? Okay. So I want you to look at the system here. We are quite efficient. If you look at today's current generator today, if you power from in your home, they are like 22% efficiency. Our efficiency is 45 to 50%. And if you combine the heat, we are basically 94% efficiency. We have noise-free system. Our system is very scalable and is very modular. We also connect everything through the digital layers. So you can monitor your systems from anywhere, from your iPhone or Android phone devices. And everything what we do is in the cloud. Okay, and our system today runs on natural gas, biogas, and propane. And in future, it will support the green hydrogen. The next slide is, this is our current 1.5 kilowatt system. We have 600 of them running in Europe right now. We have so far 3 million hours or more than 3 million hours of experience with these systems. This current system, which produces 1.5 kilowatt powers and it produces 2 kilowatt hour heat. Today, we are using natural gas. We can also run the hydrogen. we can modulate the system from 100% to 30%. So at night time, when you don't need enough a lot of power, you can bring down to 30% efficiency. As I mentioned before, we are basically 95% efficiency. It does not produce, any of the carbon footprints. So this system is very good for the 2,000 square feet house, and if you look at the average house in the United States, it's 2,500. If you need more than, if you have a bigger house, you can put 2 or 3 systems. And you will see in my next slide that, one of the places in Europe, we have installed 3 systems in one of the commercial building. Any question on this slide? Okay.
Yeah, so Suresh, explain to me,
Please.
in terms of, like most of the houses, residences, the residential use,
Yeah.
You have heating duct system that
Yeah.
carries both hot air as well as the cold air. How does
Yeah.
this fit into an existing infrastructure?
So I think, if you my system, if like my house right now, I have oil heating system. So I have oil tank and then I have a boiler. So this system is basically replace the boiler. And you can still keep everything what you have. It will produce the heat, and I will pass the heat from here to your existing ducts. And you have thermostat to control.
Yeah, but isn't that oil heating usually you may not have the forced hot air, right? You may have water heating or steam heating.
No, my system right now is air. If you look my boiler, and we have this system running right now in Ohio, and we put this in big warehouse, and they have again, a current infrastructure for cooling and heating, and we just plug into their infrastructure. It does retrofit. Yeah.
Yeah. Thank you. Thank you.
Mhm. And we are planning to migrate this thing to green hydrogen, and it also support the biogas and it support the propane. So again, you can see that, what we are trying to do to produce the power and heat and hot water using biogas or natural gas, and our system can produce power and heat and hot water. We can also work with the microgrid. If you have solar panel, we can connect with the, your battery, and you can also connect with your current, grid, and our system can work with all of this thing as a microgrid. So you can have a solar panel, battery, and fuel cell, and your current, grid to support your house, and we can work together in as a one system. And the system is very small. If you look at the size of the system, it's not bigger than what you see today, your boiler in your house or the hot water tank. We have one system running in Ohio in one of the warehouse for last 11 months now. And anybody want to see this thing, please let us know. You're most welcome to come and visit us. And next couple of months, we will have a couple of systems running in Ohio, Virginia and Washington, D.C. As I mentioned to you before, that our system can scale to the bigger system. We can also produce the same technology what we have, can scale to 50 kilowatt, 100 kilowatt systems. We have one system today running in biogas in Finland with the 50 kilowatts, 52 kilowatt systems. And if you put 5 or 10 together, you can have megawatt power plant. These are some of the examples you can see in Europe. We have one multi-story home. We have 3 CHP systems running, and you can see they also running one system at the 50% efficiency. We have commercial and living place where we have one CHP and solar panel. And we have guest house and spa where we have one CHP system. And then we have apartment block for students. We have 3 CHP systems running there. So my goal is to bring this technology from Switzerland and Germany to United States. I am in process of raising some capital to build a manufacturing plant somewhere, in New Jersey or Massachusetts or Ohio, and assemble the system here. There is no technology work need to be done. Everything is done. I want to assemble the system and then put into market after I get certification done and then support the system. That's my goal. Any questions?
I have one question
Please.
about hydrogen diffusion from connections between pipes and valves. Has that been cleared up, or is hydrogen leaking from different threaded connections as well as valves?
So I'm pretty sure the people who are building hydrogen tank and people who are building the hydrogen production systems, they are putting a lot of energy and time to make sure that it does not create any challenge. Okay, they are working very hard. There is a hydrogen tank now. You can also compress hydrogen, liquefy hydrogen. A lot of work is done in hydrogen space. Right now my focus is at this point. I'm trying to bring a natural gas and biogas system to assemble in the United States. Everything what I'm doing today is in Europe. And every time I get the system delivered from Europe to here, I spend $3,000-4,000 on the shipping cost. So I'm trying to bring the whole assembly plant, manufactured here, so that I can slowly evolve to the green hydrogen. But people who are working on green hydrogen technology, they are really working very hard to make sure for the auto industry or for the home market or commercial market or data center market, make sure that it does not create any big problem. It's a bomb, basically. We want to be careful. But people are working on this space very hard to make sure that it is bulletproof.
Suresh, do you need, you said a gas connection. What if areas where there don't have gas connection, that's where you use the propane gas?
Yes. You can use propane tank and you can use this thing, to run for just like you're using propane for cooking, right? You can use the same tank,
Right.
to warm up the house and the power also. Yeah. Or if you have big farm, then you can use biogas. One of the things our system does is produce the heat and hot water, and you can use this water. It is not a drinkable water, but you can use for septic or you can use for the gardening.
I was thinking you produce electricity also, right?
Yeah.
Electricity and hot water.
Yeah. We produce electricity, heat, and hot water.
How much does it go for now? If we're
Right
bringing it from
now,
Europe.
I'm selling the system today is less than $20,000. The FOB Switzerland, but then there's a $3,500 for shipping cost and custom duty and all those things. So it's less than $25,000, and there is a subsidy now, around 40% subsidy from government. So you're basically paying for less than 15K.
Who gets the subsidy?
And customer get the subsidy.
So they have to apply for it.
Yeah, there is I'm working through this paperwork, try to understand how. Yeah, yeah. We have this system is certified in Europe. It's called Kiwi certification is done in Europe, and in Europe we are also certified for PACE program. PACE program basically is European subsidy. They give you 50%, save cost to system in Europe.
Is that price the installed price, or is that the cost of the equipment?
Equipment cost. I think there is like $1,000 it will cost you, because we can install this now in less than half a day. If you have a, everything ready, we can bring this thing, because it takes 4 hours to warm up the system. The other 2 hours, we can connect 2-3 pipes and we are done. And everything is in cloud. We can monitor, control everything through the iPhone. And we collect a lot of data, so we can monitor the system 24/7, 365. So we see something strange in your system behavior, we have full control, so we can, modulate it, or we can turn it off.
Do you have any installations in New Jersey, or you have a pilot?
No. We have a couple of it coming in Virginia. The 2 systems left Europe now. They're coming to Virginia. I have one running in Ohio. And I have 2 running in Ohio. So, but I don't have anything in New Jersey yet.
Suresh, one thing you may want to watch out is that there is a make in America or made in America provision. I don't know how that subsidies work, so you may want to pay attention to that. Yeah.
So yes, and again, like you say, I really want to assemble here. I really want to bring this whole thing, because it's no point for me to assemble in Europe and bring it here. I'd rather use because every component in my system, except one critical component, is called stack. Everything else is standard component. There's nothing rocket scientist about. So if you look at this system here, next slide here, only one piece is a stack which requires assembly. That's an IP, just like a motherboard. Everything else is a standard component I can buy from open market.
We can't see your screen. Please share your screen again.
Oh, okay, sorry. How about now?
Yes, it's good now. Thank you.
So if you look at this box, there are 469 components in the system. Only one component is the most critical IP we have. We have more than 150 patents on that component, or that box, that particular stack they call. And everything else is you can manufacture or assemble or build anywhere in the United States. There are cabinet, there's piping, there's standard pump. There's nothing else is that critical for me. So my goal is to first, bring the stack from Europe and then buy all the components here, 400 whatever number, and then assemble system here, test it, and then go to market.
Okay, any more question? Thank you,
I
Suresh.
really appreciate Paras. Thank you very much. Please let me know if I can be any help. And I'm looking for a lot of help from every part of the country. Please, if you see any opportunity for us to work together, I'm a one-man band right now in Boston. I have office in New York. So I'm looking for a partner. I'm looking for help.
Wish you all the best.
Thank you,
thank you very much for your presentation.
Thank you.
I would like to ask Paul to share the screen and go with his presentation.
Hi, everyone. Can you see me?
Yeah, I can see you.
Okay, let me share my screen. All right, can everyone see the presentation?
Yeah.
Yes, I can see.
Great. So first of all, I'd like to thank you, Paresh, for inviting me to speak today. My name's John Paul Kiesel. I'm the territory manager for WaterFurnace and GeoStar. We're one of the largest manufacturers of ground source and geothermal heat pumps for residential and commercial applications in North America, I believe in the world. So my contact information is right there on this first slide. I'm going to post it in the chat in a little bit. So if anybody wants to reach out to me, please feel free to. So geothermal and ground source heat pumps, a lot of people seem to think that it's a relatively new technology, but really the first geothermal system was invented in 1912 and is on a Swiss patent. And open loop geothermal systems have been used successfully since the 1930s. So here we have an example of a geothermal heat pump called the fireless furnace. This was in an article in Life magazine, as you can see here, on October 25th in 1948. So with geothermal and ground source heat pumps, as the name indicates, we're using the earth as an energy source. So during the heating season, we're taking heat from the earth and moving it to the home. That's called heat of extraction. In the cooling season, we're using the earth as a heat sink, and we're taking the extra heat from the home or the structure, and we're rejecting that to the ground to be stored, essentially, to use at a later date. So the earth absorbs almost half of the thermal energy that hits it from the sun. So essentially, we're tapping into that and using the ground kind of like a gigantic heat battery. So the basics of a ground source heat pump system, the earth loop is really kind of where the magic happens. That's how we're able to exchange the energy with what's essentially an infinite energy source. The earth loop is placed either in the ground horizontally or vertically, or it can also be placed inside a pond, a lake, or another adequately sized body of water. So our factory, for example, is based in Fort Wayne, Indiana. That's where we make all of our equipment. And we have the whole operation is run using ground source heat pumps, and we have a big lake loop that runs the whole facility. So a water and antifreeze solution, also called a brine solution, is going to be circulated through that piping, so we can transport heat to the heat pump during the heating mode and away from the heat pump during the cooling mode. The heat transfer takes place inside a water to refrigerant heat exchanger called the coaxial heat exchanger. So we differ from our cousins in the air source heat pump world in the means that we use to transfer this heat. So if you put your hand inside an oven that's 180 degrees or so, as long as you're not touching the sides, you can leave it in there for a pretty long period of time. But if you put your hand inside a bucket of water that was 180 degrees, you'd really see how quickly the heat transfers using the water. So it's a much more efficient means of transfer. Here we have an example of a coaxial heat exchanger in cutaway. You could see a detailed photo on the right there. So, and here we've got a shot of the same coax heat exchanger from the end. So the water or brine solution is going to run through the center of that twisted copper pipe. And then the refrigerant is going to be circulated between the copper pipe and that outer wall that you see there. So essentially, it's very similar to a flue pipe that you would see for maybe a condensing boiler or furnace. Both are running through it at the same time, but they're not coming in contact with one another. So a lot of times people will ask me, well, how can you heat a home when you're taking heat from, the ground, which is, once you get down far enough, it averages about 50 degrees and it pretty much stays there all year round, not influenced by the outdoor air temperature. And by using refrigerant, a state of change, and being able to manipulate pressures, we can do that. So 1 BTU will raise 1 pound of water by 1 degree Fahrenheit. But then once you hit 211 degrees, to get it to that boiling point and to that state change, we need much more energy, almost 1,000 BTUs, in order to get that liquid to turn into a gas. And that is where you get that massive energy release. So, with refrigerants, in conventional, in residential equipment right now, 410 is the preferred refrigerant. That's going to be changing in a few years, but we'll use that as an example right now. At 10 psi, it will boil at minus 41 degrees Fahrenheit. At 500 psi, it's going to boil at 134 degrees Fahrenheit. We're able to manipulate the energy release and absorption of energy at different points in the refrigerant cycle by using metering devices, condensing coils, evaporator coils, compressors, those sorts of things. So here we're going to is an example of what the refrigerant cycle looks like inside of a water source heat pump, and I'm going to equate it to something that most of you are probably more familiar with. So over here on the left, we can see the air coil, and that's going to be the equivalent of the air coil that you would have sitting on top of the furnace in your basement or mechanical room, for example, or in the air handler in your attic for your air conditioner, maybe. The big difference, though, with ground source is the coaxial heat exchanger, as I've mentioned before, and this coax over here is going to be connected to the ground loop. And what that equates to in a conventional system is like your outdoor condenser coil over here, which is what's used to exchange the heat in your conventional air source kind of system. Obviously, the compressor unit is going to be in the conventional system on the outdoor unit, but in our equipment, the compressor is going to be inside the house. So ARI has designated the efficiency ratings for water-to-air heat pumps and water-to-water heat pumps as just water source heat pumps. We use EER, or energy efficiency ratio, and that's basically what it is it the BTU output divided by the power watt input. That's going to be your rating for your cooling operation under steady state test conditions. And then on the heating side, we're using coefficient of performance, also known as COP. And that is that's just the BTU output divided by the BTU input. So that's heating operation under steady state test conditions. And just to kind of give you an idea, your toaster, electric baseboard, any standard electric resistance heat has a COP of 1, meaning it's 100% efficient. We're getting every bit of energy that we're putting into it back as thermal energy out. By using heat pumps and refrigerant, we're able to explode that. And with ground source heat pumps, we're getting COPs. Our equipment goes, our most efficient equipment has COPs as high as 6. So for every 1 unit of energy you put in, you're getting 5 free units back from the earth. Over here, we've got some examples of geothermal loops. There's closed loops, your horizontal loop, vertical bore, or a pond or a lake loop. And then there's also your open loops, which use well water. So on the left, we'll see the example of a horizontal loop. This is an example of a pond loop or a lake loop. And then this is going to be your vertical bore over here. The features of your typical earth loop are going to be the circuit piping. Okay, there's going to be multiple circuits typically, and those will be either trenches or bores for a vertical application, which is typically what we're going to see more of in New Jersey, in North Jersey in particular. It's almost always going to be a vertical bore, and the amount of circuits is going to be sized based upon the capacity of the equipment and what the structure requires. There's also the header pit, as we can see over here. The supply and the return piping, which is going to be the piping that goes from the unit to your circuit piping, and then your foundation penetration, and then inside you'll have your flow center or your pump, as well as your heat pump equipment. So the piping material that's used to construct a geothermal heat exchanger, we use polyethylene pipe, HDPE 3408. It's SDR11 rated. IPS sizes of 3/4 of an inch in diameter and up. All connections are done using heat fusion at 500 degrees Fahrenheit. So there's no mechanical connections. And essentially, when you've got piping that's properly fused, you have one continuous piece of material with no opportunities for leaks at any of these connections. HDPE 3408 is one of the highest rated materials for stress crack resistance. It's made of a carbon black material that provides UV protection from the sun. So when it's on the job site, a contractor doesn't have to protect it from the sun. So it does, so there's no degradation in the material integrity from the UV rays. And it can elongate to 6 times its original length before any sort of pipe failure. So it's an extremely durable material, has a life expectancy of 100 years or more. These are some examples of your typical pond loops and lake loops. You've got coils. They can be made in mats. There's these types of vertical stainless steel heat exchangers. There's one company that we partnered with before called Slim Jim that makes these sorts of heat exchangers that you can sink in a lake. Essentially, for a lake loop, you want to have it at a minimum depth of at least 8 feet, and you need to keep in mind that that is going to be at the minimum, like the lowest level. So if you're putting this in a lake, and for example, last summer we had a pretty bad drought in New Jersey, and levels in lakes and reservoirs dropped considerably in some areas. So you want to make sure that that you've got these lake loops submerged at an adequate depth if this is something that you're going to choose. Then we have open loops. So some key considerations when you're thinking about an open loop system. Number one is going to be an adequate water supply. So we're going to want to have a flow rate of a minimum of 1.5 to 2 gallons per minute per ton of capacity, in addition to whatever the domestic requirements of that household or structure are. We want to have good water quality flowing through the equipment. So if you've got a well at your home and you notice that you get a lot of calcium and lime scaling on your faucets and aerators, you can imagine that that's also going to be building up on the inside of the equipment, which is going to reduce the life of the equipment as well as the efficiency of the heat exchange. So we want to make sure that we have good quality water flowing through this to protect your equipment and to make sure that it's operating at its peak. And we want to make sure that we have an adequate discharge location. So some examples of adequate discharge locations, maybe a drainage ditch, a field tile, a nearby pond or body of water, an injection well, something like that. And it's going to vary depending on codes and DEP requirements. Typically in New Jersey, when I see open loop designs, there is a loop there's a well that we're taking water from, and then a second well that we're injecting the water back into. So you're going to want to check with your local code officials about what to do. So here's the big question that I always get: what's the best loop? It's a pretty simple answer, really. The best loop is the one that's going to meet the capacity and comfort requirements of the structure and the equipment for the lowest installed price. They all work They all work great. It's just which one is going to meet your particular requirements. So just like everything else in life, the answer is it really depends. Depends on the specifics, right? So in order to design a loop properly, because if you've got a geosystem with a poorly designed loop, it's not going to work. And that's not because the equipment is not right. That's bad design, right? So how do we properly design a loop? WaterFurnace, we have this this program that we use. It's called GeoLink Design Studio. This is for residential applications. There's different software available also for residential applications, and you'll want to use different software for commercial applications as well. But by using the proper software and coming to the table with a good load calculation on the structure, we're going to ensure that we have a proper loops, a proper loop design that's going to generate. So GeoLink Design Studio, for example, it makes sure that you have the right loop design. It gives you operating cost comparisons. It'll demonstrate financial scenarios, cash flows. It'll calculate pressure drops and pump sizing. It'll tell you what your loop volume is, how much antifreeze you need to have in it, all those sorts of things. And it really is an excellent design tool and a necessary design tool. Using rule of thumb on something like a loop is a very bad practice, and it can be very expensive to fix if you short loop and you don't have the proper capacity. If we've got some extra time, I've got an example of a report that I generated using GeoLink, so maybe we can go over that in a little bit.
Yeah, you can do that.
Yeah, okay. So some of the key benefits of a geothermal system to homeowners, obviously energy savings for heating, cooling, as well as options to supply domestic hot water, quiet operation, less maintenance. One of our systems, really, there's hardly any maintenance to it at all. All you need to do is change your air filters, make sure that the air coil is clean, make sure that the condensate drains are clear, and that's pretty much it. You don't have to check refrigerant levels. You don't need to clean an outdoor unit because there's no outdoor condensing unit required, which means that you have a much longer life expectancy, almost double of what a conventional system life expectancy is. So a conventional system, ARI rates them at about 12 to 15 year average life. A geosystem is typically going to have about a 25-year life expectancy. I frequently get calls from my customers looking to replace units that are 30 years old and older. They're safe and they're clean. There's no combustion. There's no flames. There's no fuels. There's no carbon monoxide. It's one of the most environmentally friendly products that's on the market, and it's going to decrease peak demands for electricity. Some of the benefits of our systems to the HVAC contractor is it allows them to be competitive and offer products that are traditionally dominated by fossil fuels or in gas-constrained areas. So, we're starting to see this more and more where gas utilities are not expanding into certain areas. This is happening in New York, it's happening in Massachusetts, it's happening in Connecticut. It's starting to happen a lot more across the nation. So this offers an alternative for folks who are in gas-constrained areas but want to have electric heat. It's a higher job price tag, so that means higher profit margins for the HVAC contractor, simple operation and maintenance for them, and it allows them to offer a product that has cutting-edge technology that's going to appeal to the modern consumer. So some of the benefits to the utilities. The EPA has found that ground source heat pump systems can reduce energy consumption and the corresponding emissions by over 40% compared to our cousins in the air source heat pump world, and by over 70% compared to electric resistance heating with standard air conditioning equipment. Benefits to the electric utilities. Obviously, there's peak load reduction. It allows the electric utility to have overall load growth with consistent 12-month demand instead of just having to build systems for worst case when we have our summer peak, for example, in New Jersey, but then demand drops way off in the winter. When you've got more people heating with electric, we're going to have a winter load that is greater than or equal to that summer load. So it's a more consistent demand for the utility. It's a renewable energy and it gets credit for that from the federal government. So one ground source heat pump equals 30 or more thermal renewable energy credits per year. It's an alternative renewable energy to solar with no net metering. It's the most efficient equipment that's available on the market with EER ratings rating between 20 and 53 and COP ratings between 3 and 6. And yay for the electric utilities. It allows them to sell more kilowatt hours. So that's good. Opportunities for gas utilities. So as we transition more towards beneficial electrification and more away from fossil fuels, thermal owned loops and district loops are an opportunity for gas utilities. So Con Edison in New York, Eversource in Massachusetts. I know that both of those utilities are doing some pilot programs with district and thermal loops that would be utility owned. So this would allow for product diversity, which equals more financial security for these utilities as they go forward. It's another product for them, another thermal product for them to sell and for an asset for them to own that that property owners can tap into and pay a fee for that use. It's a durable asset for recurring revenue, again, with that 100+ year loop life. And there's some generous tax benefits from the IRS also. Excuse me. So some interesting facts about Geo. If 1 in 12 California homes install the Geo Exchange system, the energy savings would be the equivalent of 9 new power plants being built. Installing a Geo Exchange system in a typical home is equal in greenhouse gas reduction to planting an acre of trees or taking 2 cars off the road. Current Geo Exchange installations equal over 14 million barrels of crude oil saved per year. And as I said earlier, the ground absorbs 47% of the thermal energy from the sun that reaches the earth. This amount of energy represents more than 500 times more than humanity consumes each year. So at this point, I'd like to again thank you all for your time and encourage you, call me, text me, email me, follow me on LinkedIn, connect with me, join my New Jersey Geothermal group, which Paresh is also an admin of. We need the support of men and women like you, engineers, people in the utilities, people in the Board of Public Utilities, the Department of Environmental Protection. We need all of you so that we can transition towards a clean and green future in New Jersey. Does anybody have any questions for me, or do you guys want to take a look at maybe the that report that I'd mentioned before?
John Paul, if you don't mind, I have a question. Yeah, a couple of questions.
Yeah, go ahead. What's that?
One is that for the submersible pumps for the loop, can you use detention ponds?
Yeah. And as long as the body of water is large enough and deep enough, you can put a pond loop or a lake loop into it. Any body of water. It doesn't need to be a pond or a lake. It could be a river. It could be a bay, as long as it's allowed by your local building department and the Department of Environmental Protection. As long as you're following those rules in terms of thermal energy transfer, yeah, it's going to be fine.
For wells, you need two wells, right? One for the intake and one for the outflow, right?
In New Jersey, that's typically what we see. Yes, there'll be a well that you take the water from, and then a second well that's drilled that you inject the water back into so that you can recharge the aquifer.
So this is for recharging aquifer. There's no contamination, anything like that, right? Yeah.
No, it's just running through a pipe and going right back out. It's a copper pipe. It's not being mixed with anything.
I see. I see. In terms of so all these loops are going to be under the frost line, so you don't have to worry about any kind of freeze and frost, right? Yeah.
Oh yeah. So in North Jersey and so my territory, what I cover all of New Jersey. I cover the downstate portion of New York, Connecticut, and Rhode Island, and pretty much all of the loops that are installed in this area are vertical bores. Some of them go as deep as 500 feet. But when you're doing a horizontal loop, typically those are going to be around 6 feet down, and that's going to be below the frost line. But the deeper you go, the more consistent the temperature is of the ground, and the less influence you're going to see of that ground temperature, meaning a smaller swing back and forth between seasons. So, you know, in the summer, you'll see less of a temperature swing, and in the winter you'll see less of a temperature swing. It'll be consistently around that 50-degree mark. So I just posted my information in the chat if anybody wants to grab it there. That's my cell phone, my email. You guys can find me on LinkedIn also. But let me share. Do you guys see this report on the screen right now?
Yeah.
Yes.
All right, let's see. Let's do that. So this is a GeoLink report. This is just an example of a report that I generated. It's fictional, but it's realistic. Okay. So let's see here. So what I did in this one is I'm comparing one of our 7 series, which is our flagship product. It's a variable speed compressor with a variable speed blower and a what's called a desuperheater. That's going to be a hot water assist that basically rejects heat from the compressor into a smaller coaxial coil, and then that water is moved to your domestic hot water tank. So we're preheating the hot water that's going into your domestic hot water tank. So we're reducing the delta of bringing that tank temperature up to whatever temperature you want. So for example, groundwater is coming into a home usually around 50 degrees or so. And then in residential applications, usually a hot water heater is set around 120 degrees. So that's a 70-degree delta. By preheating that tank, we're reducing that 70-degree delta to something down much smaller, and we are increasing the amount of hot water that you can use, and we're reducing the amount of energy that it requires to get you there. So we're comparing our variable speed product over here with a vertical bore. This is an example of the loop field that's being used. And what we're doing is we're comparing that to the base system in this fictional home, which in this case is a 5-ton, 10-SEER conventional air conditioner with R22 and an oil furnace that's 120,000 BTUs with a PSC blower. We're comparing that to what is arguably a very efficient and good system, a 19-SEER 5-ton air source heat pump, variable speed, hybrid system with a 98% efficient condensing furnace using propane as a fuel. So we are in GeoLink, we're able to put in utility costs. So what I'm assuming in this example is a kilowatt hour rate delivered to the home of 26 cents per kilowatt hour, which is probably pretty average for most of New Jersey. We are looking at a fuel oil rate of $5.50 a gallon is what this person was paying for their oil in the middle of the winter, and their summer rate, I was assuming $4.25. and we're assuming a $3.50 per gallon rate for propane. So these are pretty realistic costs that I'm assuming in terms of the utility. And this program uses 20 years of historical weather data, and it's running the same system. It's running each system through that same simulation of the last 20 years using those fuel rates. So it's a realistic. It's going to give you realistic costs. So using these assumptions and this system design data over here, what we're finding is that my 7 series equipment has a total annual operating cost of $2,762. So that's $1,500 for heating. That's $138 for cooling, and $1,000 being delivered to your hot water. Oops. Let's see. Good. Can you guys see this better? Maybe this is a little bit more clear. So here's the operating costs. Using the air source heat pump option, or the air source option that I was comparing to, we're looking at an annual heating cost of $2,500, an annual cooling cost of $1,700, for a total operating cost of $4,700, $2,000 more than mine. Compared to the base system that we're assuming exists in this fictional home, using oil and a 10-SEER air conditioner, total operating expense of almost $8,700. So it's a pretty considerable savings. And it'll give you all different kinds of charts and graphs, because people like charts and graphs. It makes everything visual. And then over here, this is really my favorite part of the report that gets generated. It gives you a full performance summary. So it tells you about the equipment, it tells you about the loop, it tells you about your loop performance over here. So this is something that's really important. It tells you how to size the system. So what we were assuming with this loop design was that we have 500-foot bores. The total bore required to deliver the required BTUs for this system is 1,000 feet. So we've got 2 bores at 500 feet deep. The average depth is 250 feet of that bore. Of the average depth is 250 feet. The minimum temperature that this loop is going to reach is 33 degrees Fahrenheit. And the maximum temperature that this loop is going to hit when we're rejecting heat in the summertime is 72 degrees. So like a good loop is going to perform in this range here, somewhere between 30 and 90 degrees. So your maximum extreme temperature should be 90 degrees or less, and your minimum should be 30 degrees or more. If you start going below that minimum temperature or above that maximum temperature, what happens is you can start, it's called taxing the ground, where you could either freeze the ground or you can heat it so much that you basically cook it and you get rid of all the moisture around it. So having a proper loop design is extremely important. And then over here is a detail of the summary that that we were talking, that I showed to you before. Let's see. So this is some information on the pressure drop of the loop. So in here we plug in the information on the loop. So we've got 2 500-foot bores. We're using 1.25-inch pipe. The supply and the return piping is 1.5 inches. So these are just some of the details that you can plug in as you design your loop so that you can make sure that it's performing correctly. And you don't need to, so like, for example, if I was using 1-inch pipe over here instead of 1.25 inches, I would probably need to have an additional bore, and I would require a bigger pump, which is going to use more energy to move the brine solution through the loop. And then we've got some pressure drop charts over here. And then this is the bin data stuff. So there's all kinds of like really good information in the program over here. And then there's one other thing that I wanted to share with you guys also. This here is, so this is a product that we have called Symphony. What Symphony is Symphony is a monitoring device that we can put onto, it's an accessory. This is not on all of our heat pumps, but it's an accessory that's available for almost every heat pump that we have, on the residential side in particular. And this allows for energy monitoring for the homeowner. It allows them to have remote access. For the installation contractor, it allows them to monitor system performance. Symphony is connecting or collecting rather over 100 data points of information every 10 seconds and recording that. So you can see detailed graphs, which is really great if you have maybe there's issues like intermittent lockouts or things like that that are happening. It allows the contractor to remotely see what happened at the particular moment of failure. It allows them to remotely troubleshoot it. It even allows them to remotely repair it in some cases. And in the user agreement for Symphony, we also have some language that allows for the utilities to view some of this data for their reporting purposes. So if you need to report and you want to see, like, instead of use assumed data, you can use actual data. This is actual data. So as you can see, every one of these blue dots is an active Symphony system that's been running in the United States. There's over 12,000 that are running in the United States. You can drill down and get much granular. So let's go to New Jersey here. In New Jersey, there are 283 systems that are currently running using Symphony. We can filter over here. So I've plugged in a 25-cent kilowatt hour rate. And this is looking at all the units that are running in New Jersey right now. So based on all the systems from 1 to 6 tons that are running in New Jersey with that 25-cent per kilowatt hour rate, we're looking at annual heating cost of $925 and an annual cooling cost of $279. We can even get more granular if we want, and we could say, I just want to look at 5 series dual capacity units and 7 series variable speed capacity units that are 5 tons. So when we're looking at that data, go back. So when we look at that data using those slicers, there's 54 of those units that are running total annual cost of $1,600 or an average of $136 per month for homeowners to run them using the assumed input again at 25 cents per kilowatt hour. So there's some really cool stuff, and it's like I said earlier, we need the support of men and women like you all that are listening to me right now, so we can see more adoption. I'd like to see 5,000 of these units in New Jersey instead of just 54. So and this is a way that we can really move more towards grid stability and move away from fossil fuels and more towards electrification. So that's all that I have right now. If anybody has any questions, let me know. Otherwise, please, like I said, email me, text me, call me, connect with me on LinkedIn, whatever works for you.
Okay, so we are good here. Mr. Kwaku.
Hello, everyone.
Jyamfi.
Let me just share my screen and we'll get to it.
I would like to say for him, he's a chemical engineer, very celebrity engineer. And really, I'm very happy to have him here.
Thank you, Paresh. I appreciate that. Thank you so much for having me. It's great to see everyone. It's great to see Suresh too again. Good to see you, Suresh. Hope you're doing well. Great to see all the members from BPU, DEP, DOT, and others. And a really good presentation, John. I enjoyed that. And yep, my name is Kwaku. You can call me KJ. I'll put my contact info in after I do the presentation. I'm the CEO and co-founder of Farm to Flame Energy. I'm a New Jersey native. I was born in Edison, New Jersey. I grew up in West Orange, New Jersey, where Thomas Edison made many innovations. And very grateful to be supported by New Jersey with our problem-solving technology. So at Farm to Flame Energy, we provide smokeless and odorless renewable power at half the cost of diesel. So the global problem we're solving is around diesel generators. Over 700 million people in the US and around the world rely on expensive and dirty diesel generators for constant power. It's a $23 billion market, and diesel historically costs 3 to 4 times the grid price. And due to the conflict that increased in the Ukraine and Russia over the past 12 months, that price has even gone higher. And so it's a really expensive alternative to our regular grid electricity, which is supported by a vast mix in the US. And the toxic smoke that comes off diesel exhaust emission kills many people every year in the form of that carbon monoxide and the black smoke. So the solution we've built is the FTF generator. This is a carbon neutral electricity asset that is just as reliable as diesel, but half the cost, with no smoke and no odor. And it's built into a shipping container for portability, the ability to raise the generator up above sea levels during storm surge events, and just as a hybrid model for those who need reliable power. And we use several energy feedstocks in our generation process. We pulverize them, and that's how we're able to burn them smokeless and odorless. These feedstocks include corn stalks, wood waste, miscanthus, paper waste, and more. And one of our 30 kilowatt generators can power 3 homes, a commercial building, or a medium-sized farm. And so we've actually built this generator. This generator on the right is the FTF 30 kilowatt generator. We built that at Kearney Point in Kearney, New Jersey. And we were very grateful to get funding from the EPA, the U.S. Environmental Protection Agency, as well as the New Jersey Board of Public Utilities partnered with the New Jersey Commission on Science, Innovation, and Technology to build out this generator. And this generator has actually allowed us to enable our combustion process. Our patented combustion process helped us burn fuel smokeless and odorless. But it wasn't until we started building this that we actually achieved the blue flame, which is pretty much unseen in the biomass to electricity industry. This is very unique because it means we have a low carbon monoxide compared to a lot of biomass combustion. And that's really because of what we do on the fuel treatment and fuel processing side to get that higher combustion efficiency. And we're cheaper than existing options. We're cheaper than diesel by half, solar plus storage by 2/3, as a battery paired with the panels prohibits cost-effective baseload power. We're cheaper than anaerobic digestion by half. Our generators operate at 14 cents per kilowatt hour with no methane, no conflict minerals, and no toxic emissions in our carbon neutral supply chain. And speaking more on the fuel processing side and what we do to achieve a high combustion efficiency. So we're using a wide range of feedstocks, but the main component is our fine grinder. This fine grinder allows us to grind down sawdust-sized material finer than powder. So we're essentially grinding it to under 104 microns in particle size with an 80% distribution under 60 microns. And this allows us to disperse the fuel in air and atomize it, pretty much burning all the fuel. That's a big problem with biomass generators and gasifiers, is that their particle size is variable. So you could be burning 1 to 2 inch wood chips, and you may be burning the outside of the wood, but there's also a lot of moisture trapped on the inside that you can't burn. So you form tar, carbon monoxide, and it really does not help when it comes to thinking about EPA emissions for CO, NOx, and SOx, and also DEP as well. So these are really important points of what we do. And we began talking to the DEP in New Jersey about this in 2021, and they were very excited as well. And the next thing on this is actually the dryness of the material. So you have the particle size, but you also have the moisture content. And we utilize, yes, yep. And we utilize a rotary dryer to dry down under 5% moisture content. And so that's what also allows us to achieve that high combustion efficiency. And furthermore, we're using machine learning. We're using LiDAR imaging for fuel quality assessment. This is basically for streams that are heterogeneous in nature, maybe from a landfill or impurities from a sawmill, for example. We can remove non-viable components like plastics, glass, rocks from the feedstock, and this can help us increase our revenue by increasing the fuel stream purity. And we make money with energy as a service agreements, also known as power purchase agreements. So this agreement costs the customer 14 cents per kilowatt hour on average, structured just like the utility bill you receive at the end of the month. It allows us profit margins of up to 40%, and the customer does not have to pay the down payment or the capital costs on the equipment, but instead they experience savings on their current solution for an over 10-year contract. And our average PPA or CHP contract goes between 10 and 20 years, and that equals $250,000. And we have $1.9 million in the pipeline for 2023. We're right now doing a project with Georgia Pacific. Georgia Pacific is the third largest paper maker in the country, and they are the largest biomass electricity producer in the country because paper waste is pulped wood. So they have all this wood that they're using to power their energy intensive paper making processes, and they sell the remainder back to the grid. So they saw that we were doing a high thermal efficiency project, and they wanted to partner with us to include this in their paper dryers, basically converting their paper dryers from natural gas to farm to flame paper dryers that use their own sludge to dry their paper. So it also creates a circular loop for their economic model. And it's a waste diversion initiative for carbon neutral electricity generation. And we're working with Think and Grow Farms, and they're in Millville, New Jersey. That's where this 30 kilowatt generator is going, as we signed a PPA with them that will allow us to abate 237 tons a year of carbon dioxide from diesel generators. And we also have a generator installation for the Syracuse Center of Excellence, who has funded that generator. That was a grant that also helped us get it up. And we have a great team of co-founders on the top, and this team has built the Farm to Flame generator. We've been funded by world-class organizations, including Georgia Pacific, Cisco, the US EPA, and New Jersey BPU for over $1.6 million non-dilutive. And we have a great team of advisors like Mark DeSantis, who has had his first company in wholesale power generation, which sold to Moody Aldrich, a venture arm of General Electric. And he's a serial entrepreneur. He's even a CEO right now of Bloomfield Robotics. His previous company, which did image classification of road impurities like road cracks, they just sold to Michelin. And Stan Fisher, he's been in the ESG space for about 13 years. He's a Harvard Business School mentor and also a NYSERDA mentor, and he has received funding for over $200 million in his previous companies, specifically in the .com era for software consulting. And he's been a great help to us, helping us in contracts with Georgia Pacific and really go on to great commercial feats. So we're very grateful for all of our team members in this leadership, and also all of our technicians, engineers, business development members as well. And so if you have any questions at this point, I'm happy to answer, and thank you so much.
I have a question about post combustion processes to get rid of any sort of emissions such as particulate matter. Is this required for the system?
Yes. So we have to get rid of these emissions and the good thing about this is that it's smokeless and odorless, it really just means there's a low ash content. But with that being said, there's still particulate matter, and we use a ceramic filter. The reason why we use a ceramic filter instead of an electrostatic precipitator, which is commonly used for biomass stack, is because it's not expensive. It's not operationally expensive, and it's not capital expensive. Electrostatic precipitators, you have to have a power source. It's basically a positive and negative plate that attracts, well, the positive plate is charged and it attracts the negative quote unquote ash to that plate and collects it and discharges it. A ceramic filter has a partial positive charge inherently, and so that's why we've decided to go that route. Now, at scale, it could be different when we're doing larger megawatt projects. You could have a baghouse filter. You could have many different filters at scale that are also passive and less operationally expensive, but right now we're doing the ceramic.
Do you sell your system?
Yeah, so we sell the system to corporate partners who have the capital means to buy it. But for smaller companies or medium-sized companies, we can leverage equipment financing. Ultimately, the corporate partners do leverage equipment financing as well, but we can leverage equipment financing in a model that has farm to flame keep ownership of the generator, but enables the customer to experience savings from day one. So they can experience savings as a in the form of a power purchase agreement or a combined heat and power agreement.
I'm talking about the residential purchase. Some three people get together, say, hey, we want to buy this. You have a lot of leaves and debris of trees coming, and we want to use it.
Oh yeah, we wouldn't be opposed to that. We would not be opposed to selling a system to residential. If they would like to buy it, that's definitely something we work out.
So you don't know the cost upfront, right? How much?
Yeah, it's $3,000 per kilowatt, including the fuel processing equipment and the generator.
Okay, so like a $90,000.
Yeah, for 30, I guess, yeah.
I used to be forest firefighter, so I'm very much interested in your
really?
system.
Oh, that's very nice. That is very nice. Yeah, we've definitely been talking with public works departments. We've been talking with U.S. forestry departments, and that's an area that we're interested in, and really, making use of brush that would otherwise cause fire spread. So, being able to mitigate that. We actually signed, we signed the 2,500 ton per year agreement in Atlantic County for landscaping waste. Basically, we get the waste at no cost because it's otherwise a liability to the company. But we did something similar in California, in Southern California, where they've received the waste from Idlewild Forest, which is really prone to a lot of forest fires in that dry season. And so this is a really good incentive for areas that are trying to clean up that brush, essentially clean up that forest brush.
Very interesting. Very interesting.
I appreciate it.
Anybody else have any general question for any of the presentation?
If you have any questions, I'll put my contact info in the bottom, and I appreciate it. Thank you so much.
Yeah, you can put it in the chat also, your contact information, so it stays there forever. Anybody
Sounds
can.
good.
So I think Rupa or Jivan Jyoji is not here right now. So I would like to thank you, everybody who participated, and really very much thankful to all the presenters, because without you guys, we don't have this event. We'll be doing this kind of event more next month, whatever. So all of the people who we did not get for doing presentation today, we can get them next time. And thank you very much. And we adjourn the meeting.
Paras.
Thank you very much.
Thank you.
Thank you, Paresh. Thank you for the invitation.
Thank you very much for joining us, Tracy.
Absolutely. Absolutely. Hopefully next time I can join you for a longer time.
Oh yeah, you can help
Okay.
me out to find more presenters.
Oh, okay, I'll try. All righty. Bye-bye. Have a good day.
Bye. Same to you.
Bye. Thank you.
Thank you and for joining, and thank you for our support from DOT.